Welcome to the Todd and Noah show. Noah, Bethel, taking the mystery out of electric motors.
It's an exciting adventure.
Yeah, we've got Noah Bethel, the Vice President of Product Development, and my name is Todd Gunnarsson, the Vice President of Sales and Marketing, and got another podcast we're going to knock out here today.
I'm excited about it. Good subject matter.
We're sipping some cold brew coffee, some chocolate, coconut chocolate.
It's quite tasty.
Yeah, a little heavy cream. I have a little sea salt in mine. Noah, you don't like salt?
No,
I didn't want to put salt in yours because I didn't know if you would enjoy it or not.
It's perfect.
Good. I'm glad you like it. Well, Noah, we've talked about all the fault zones, and we've talked about some different case studies in those fault zones, but through customer request or podcast request, now we're going to talk a little bit about all the different types of motors that exist out there. And the first one is probably 90% of the population, which is induction. So it's going to be kind of a review of all the stuff we've talked about, but still, let's talk a little bit about the construction of it and what it's used for and things of that nature.
Yeah, you called it. The induction motor, the simple induction motor, is the workhorse of the motor industry. They're, as you mentioned, 90% of the motors out there, they're of that type, that model. And the construction is very simple. You've got a rotating, chunk of steel with laminations and bars, and then you've got
the Rotor.
The Rotor, nicely named.
Right.
It's rotating, and you got, of course,
the mystery out, right?
The mystery is solved.
It's mystery solved. So the rotor is the rotating part, and
right.
You also have
the stator, which is the stationary part, right? The words go hand in hand. Now, so you're talking about, 3 phases of windings wound around the stator and in a wire delta configuration, which is not that critical, but, insulated from ground, and that creates a rotating magnetic field, induces power under the rotor, and the torque pushes that rotor around. Pretty simple.
So you have a squirrel cage rotor. The design of the rotor is, like you had said, bars, laminations, shorted end rings.
Right, yeah, it's almost like you've seen those little cages where the mice get in and run around in circles.
Squirrel cage.
Literally, it's a squirrel cage.
They call it a squirrel cage.
It's amazing how they name that.
It's like they named, we were in the Navy, so yeah, they wanted to keep it simple for us.
It's simple. You can picture the squirrel cage and you can picture a rotor.
Right. So can you talked a little bit about anything to add on the operation, how it's developed, or we apply voltage and current, apply voltage to the field.
Right. So the three phase power applied to the stator is going to obviously create a rotating magnetic field based on the sine wave activity that's being pumped in. That's going to induce a voltage onto the bars that are running, amongst the magnetic fields. I think they call that generator action, right? A conductive material and a moving magnetic field creates current flow. Okay, so voltage induced on the rotor bars creates current, that creates its own field. Now you got a field on the rotor and a field on the stator, and they chase each other around.
At a slip, essentially.
Yes, one of the things.
They're slipped behind each other, and that's what creates that
exactly.
current or less current.
All too often we walk up and we're looking at nameplate data on an induction motor, right? And it says something like 1800 RPM. Well, if the induction motor is turning at 1800 RPM, there's no induction, right? You have to have a differential movement between the stator magnetic field and the rotor itself. So a lot of times that's just a product of, coming out of the motor repair or whatever, or out of the manufacturing, they're sort of rounding up. It's not accurate, but just for those guys who are, adding nameplate information to software, I think it's important to understand that an induction motor never turns at synchronous speed. 1800 is a synchronous 4-pole motor. It has to turn something like 1780, 1785.
So talk to us about some of the benefits, right, of induction motors over the other types of motors.
The biggest benefit is they're simple, right? Just kind of like what we described. It's a rotating mass of steel and a rotating magnetic field. It's very simple, and as a result of that, the cost of the induction motor is quite low. One of the things that people really like about them is you can go to a Baldor and buy a motor of a general frame, and then you can turn around if you get a better price from a GE or a Westinghouse or something like that. You can interchange these motors very frequently freely. And that's, from a market perspective, that's very comforting. You do have to, make sure that the feet and the platform and everything are going to, line up for the alignment of the shaft and stuff. But that type of interchangeability is just wonderful. The other big thing, and you and I being Navy, we've had a lot of experience on the DC side of the motors, a lot of maintenance heavy, carbon dust and brushes and all that. Well, guess what? The simple ruggedness of an AC induction motor is not that. It's very simple. The maintenance is low. Obviously, you got to maintain the bearings and the grease in the bearings and that kind of stuff. But so maintenance is very low. Overall, they have decent speed regulation. They are from the full load to no load. The speed changes are relatively small, and because of the design, there's decent overload capacity. You can start these things, and they'll take a punch. A lot of times, we're seeing 7 to 10 times in rush, so they do have some overload capacity. Again, I can't say enough, no brushes or slip rings, right? So you don't have to breathe the carbon dust and any of that. They're easy as a result of their simplicity. There's no arcing and sparking from the brushes. A lot of people use these in explosive or hazardous conditions. So, and overall, they're fairly high efficient. So the cost to run them is as good as it's getting. They're getting up into the high 90s in terms of percentage efficiency.
Yeah, because that air gap between the rotor and the stator is getting increasingly smaller.
That doesn't hurt the efficiency for sure. Yeah, that's used to be you could feel like you could stick your hand between the rotor and the stator back in some of the older U-frame and stuff, but not today.
If you have a 93% efficient motor, that is a small gap between that. So it just makes the tolerances that much more precise, or needed to be more precise, or else you could potentially have problems. And we have quite a few case studies showing where the rotor-stator relationship became too close.
Yeah, they're not supposed to be touching.
Yeah, they're not supposed to be touching. So talk to us some of the applications, right? What are they used for? What are induction motors used for in industrial applications?
You see them everywhere. Obviously they're in every walk of life and in every industrial facility. You see them very popular in fans and pumps. Okay, and that's everywhere you go you see that. So blowers, compressors, they're in a lot of places and almost unlimited in terms of their application.
So when we talk about induction motors, and like we said, we've had quite a few podcasts on how to analyze data, but what are some of the things that we would look for to analyze these types of motors? What types of parameters are we going to collect data on and make decisions on?
So like in every situation where we talk about, applying technology to electric motors, it always starts with the fault zone analysis. And, we're interested in power quality, what you feed the motor, power circuit, is the current path, is it clean of high resistance connections, insulation, stator, rotor, air gap, you've heard us say it 1,000 times. Those are really still the starting points of your induction motor. And basically the next step is, well, is it running or is it de-energized, right? So, if the motor is offline, you can send signals into the stator windings, and you're going to use those stator winding signals and analysis to actually look at the stator and the rotor. It's almost like using the coupling of the air gap to look at, use the stator sensory as to look at the rotor health. So it falls back to that fault zone.
And looking at rotor health, we do a thing called motor current signature analysis, and you really need that slip because slip is required to find out what pull past.
Absolutely, and one of the things we always express is, the slip being instrumental into the pull pass frequency, which is looking at the modulation of anything going on with the motor and the rotor and the stator together. Even a machine train can create that kind of modulation. But what's interesting is when it comes to rotor analysis, it is kind of nice to come up on a relatively steady state. If you got the load changing dramatically, rapidly, it's going to be a little harder for you to use some of the tools. You might have to fall back on an offline test to be a little bit more conclusive as far as rotor health. But yeah, load variances does play a role.
Yeah. So if we were to step through these and I were to say, okay, so for power quality, what would be a concern that we would be worried about? Is it the, I guess power quality, our concern would be temperature, right? If we're putting in too many non-harmonics to the fundamental frequency, doesn't that just create excess heat?
It does. In fact, we, a lot of times when we're giving workshops on motor reliability, we tend to relate almost every fault zone to heat. And, it's the number one killer, right, of our electric motor.
And we say it's bad because heat then kind of goes into our other fault zone, which is insulation, right? So because there's classification of temperature on that insulation.
There is, like, and you can, in fact, you can say, what is it, in classes, A and B, and you've got F and H are the popular ones. For the most part, if you look at Celsius, most of these motors are running up into the, high 100s, 150, 180 degrees C, and that's a pretty big deal. You think, well, that's should be fine, right? Well, the further you get into the windings, the hotter it gets, and so a lot of times you got to keep those motors cool. But if back to the power quality issue, obviously, if you're feeding poor power quality to the motor, it's having to work a lot harder than it should to accomplish the same work. So if you've got a 100 horsepower motor and you're feeding it poor power quality, well, it may have to work at 120 horsepower level just to get 100 horsepower. And that's where the heat comes from.
So I know on some of our power test data, you have a total harmonics and you have fundamental for voltage and current. So why would that be different? Why would those numbers be different?
So I always enjoy looking at those differences, and it really, you can look at the horsepower rating. One of the things we try to do is not only, utilize that fundamental versus total to understand how much, poor power quality we're experiencing, but then apply that to almost like a redesign of the motor, and I'll come back to that. But the fundamental is only taking into account the fundamental frequency. So in North America, 60 hertz is the fundamental frequency. So all the calculations we're doing, we're basically separating the frequencies, and we're saying, hey, how much of the work being done is done by the most efficient fundamental frequency, and that's your fundamental value. So as an example, for a 460 volt motor, you may say, hey, we got 400 volts that are actually being utilized for fundamental work, right? And the other voltages is going to harmonic content. So when you look at the total, it's taken not only the fundamental, but all frequencies involved in the calculation. And what's interesting about that is it's not hard to see. You might have a motor that's pushing, even our horsepower calculations take into account the different frequencies. So you may have a 100 horsepower motor pushing, 80 horsepower, right, according to the calculations, but guess what the current draw is? Almost nearly full load. So if you got a 120 full load amp motor that's running at 119 amps, but is only delivering 80% of the design horsepower, I always tell people, look up at the fundamental versus total, and very often it's very different.
And what about, say, for instance, the power circuit? How would we monitor just the basics? You don't have to get in depth because there is an actual podcast on power circuit. Right.
We did focus on that a lot. And I tell you, this becomes more important the older the plant, right? Yeah. Brand new plants are always at risk because, you've got brand new installations. We've had our fingers in everything, and as a result, we didn't tighten something or we tightened something too much. But, you can have a great transformer power and you can have a great motor, but if the cable run on the way is having trouble, we need to know that, right? Yeah. And that can change with temperature as well. Right? It can be a lot worse when it's hot, or it can be a lot worse when it's cold. So sometimes cold versus hot measurements are a big deal. What we always say is that, when it comes to voltage and current, it's important to remember that voltage readings are very location specific. When you connect voltage meter or a voltage measuring tool to a circuit, it's looking upstream of your connection. It's not looking downstream. That's important to know. You might have a perfectly balanced voltage, but a massive high resistance connection just a foot downstream of where you connected. That is important. Now, current is more of a burglar alarm. We talk about having kids, and a burglar alarm tells you whether they're sneaking in, sneaking out. You don't know what's going on, but you know that something's wrong.
You don't know where they're sneaking.
You don't know unless you upgrade the burglar system or the security system. But current is broad.
Do you know how a teenager is lying?
No.
When their mouth is moving.
Yeah, okay. Now maybe I have heard that actually. I can speak from that for sure. Yes, I've got that experience. But that current is it's a burglar alarm. If you take a current measurement, no matter where a high resistance connection may occur, and it may be because of a bad lug, it can be an over torqued connection, a bad crimp, all that can play into a power circuit issue. But current is going to tell you that there's an imbalance, but you don't know what side it's coming from.
Right, and all of these are kind of just in line with the cheapness of the induction motor. So you're trying to prevent that because you may not. What is the horsepower where somebody will just throw away that induction?
That's a great question, and I'll tell you it varies from industry to industry.
Plant to plant.
I've been on plants where, hey, if it's more than 50 horsepower, they're calling the local motor shop and they want it rewound. I've been to other plants where if it's under 200 horsepower, and maybe that's just the the way of the rich or something. I don't know, but it's something we can't, as a supplier of technology, we never know. And so when we're looking at data from somebody with a 75 horsepower motor, you can't think that they just want to throw it away. But yeah, we've seen up to 200 horsepower be a throwaway motor, just replace.
I mean, you said it in the benefits of an induction motor, they're cheaper in cost. So as a result of that, they're less likely to have to be dealt with from a repair standpoint, unless it's a critical asset.
Right.
So other things that we can look at is, you talked a little bit about the insulation. I know we're going to get into that more as we go into the other types of motors. The rotor is pretty basic, either copper bar or spun cast aluminum.
Right. Rotor. Pretty much that's the standard when it comes to the squirrel cage. That's the two materials that are very, very popular. Some of them are more expensive. Obviously, a copper bar.
They're skewed too.
They are skewed a lot of times. We have some very odd designs where you have literally like a split, right? So in the middle of the rotor, there's another sorting ring, basically. Now that's kind of strange, and then you start putting like a chevron and an offset on that to control harmonics, and it can get very complex, and sometimes the out-of-the-box readings.
And the nice thing about this, we always tell you to develop a relationship with your motor repair facility, because you just mentioned a whole different array of rotor types.
Oh, yeah.
And what's not on that nameplate are rotor bars.
No.
So in order to develop, to understand how many rotor bars, because it is instrumental in some of our other data collection points, say for rotor bar pass frequency, or even to help with pole pass sidebands if you need, if necessary, not really pole pass sidebands, but rotor bar pass frequency.
Oh, absolutely, yeah. It all comes back to using pole pass to calculate speed, and really it's more of a confirming piece of information. If you know what that is, then you can backtrack and say, yeah, I'm dealing with a good case study or a C story, if I could add one.
Well, do we want to?
Should we have some music? Dive. We're going deep.
Don't go deep.
Now, deep doesn't mean
at the surface level.
That's right. Deep doesn't mean we're changing the facts or anything. It just means that we're going to dive into a subject matter. So we're on the East Coast at a utility plant, right? And so we're looking at what I'm doing a test on this new Emax technology that we come up with, and I see this high pole pass frequency sideband, right? So if you imagine a 60 hertz signal with a peak on either side, if it's 1 to 2 hertz away, it could be a pole pass frequency sideband. It could be indicative of a rotor anomaly. So we're looking at this, and I'm like, oh my gosh, we got this massive pole pass frequency sideband. And I'm thinking, what a great catch. First motor we tested on this pulverizer motor is a broken rotor bar. So I'm patting myself on the back saying this is the greatest thing.
I'm gonna get a raise for sure.
I should get a raise. And so we go to another pulverizer motor right next to it. Guess what? I am living right. The exact same high pole pass frequency sideband, and I'm thinking 2 for 2 is a good number, right? But then after the third and the fourth pulverizer are saying the same thing, I started to become a little bit suspicious. I can't be living that right. No. I haven't prayed that much.
This facility isn't running.
Something's going on, right? Well, it ended up that the rotating frequency of the pulverizer mechanism was, guess what? Right at about 1.6 hertz, exactly the same as our electrical pole pass, and so it was a confusion. So we have since then had to expand, different analysis tools, looking at swirl effect and a variety of different things that you'll hear on the Rotor podcast. But it really was an eye-opener to me that, hey, you can't jump on those things. We got to filter out some of the messiness, and that's all part of knowing the speed and confirming it and using that to make good decisions.
So, and now we also have the stator, which you say is the stationary portion of it, and you say windings, and there's a whole different array of windings, how we wrap them, and concentric wound and random wound, and that you have to be aware of when you're out testing.
Absolutely.
They can affect your data.
It can, and in fact, one of the things that my eyes have been opened up a lot is when you go from like the 460 volt low voltage world of AC induction motors, most of those are, you're going to have some general specs, and they're going to send you, do I need inverter duty or not? That's kind of a big deal. In fact, most manufacturers are almost going 100% inverter duty just because it's almost as easy just to make them all. A little more expensive, obviously, but when you're doing it all, sometimes the manufacturing costs outlay that or outperform that. But that being said, when it comes to the simplicity of a low voltage induction motor, your choices aren't that you can go to a bunch of different manufacturers. There are certainly specs that you want to apply, but now when you go into the medium voltage world, the medium and high voltage side of things, But now the specifications that go into volts per turn, and one of the things that we're heavily involved with is the Electric Power Research Institute. Now that's better known as EPRI, right? And I'm you surround yourself by with either nuclear or fossil based electrical engineers that really get involved with the motor manufacturer to the point where they're talking to the team and the design of the motor and asking for specific design criteria, different wraps, different magnetic papers, and just the specs go on and on and on. It's like a book, but for good cause because they've got experience in that. So from a low voltage 460 low horsepower to a medium voltage, we're talking into the 4,000 volts, 7,200 or even 13,000 volt range. The specifications, we like to call it the birth certificate per se, is much larger.
Yeah. And then lastly is air gap, and we talked a little bit about this, the higher efficiency aspects of the induction motors, that air gap has become much more closer. The rotor and the stator relationship are much closer, so the air gap is much smaller than what it used to be in years past. And so it's important to understand, if you have any air gap issues, that you do not have a lot of opportunity to let that go for too long, because then you will develop some rotor stator rub. And we do have a couple of case studies on that, and we also have a podcast on that. So we probably won't go too much deeper into the air gap side of it. I'll just understand that the gaps have shrunk with the higher efficiency of the induction motors. So next, Noah, another motor that we do come across in the field is called a wound rotor motor.
A fantastic beast.
Or slip ring induction motor.
Yes. So when they say, hey, I need you to come up and test a slip ring motor, sometimes it's a wound rotor motor, sometimes it's not. It's always good to ask some more questions.
Yeah.
Are there 2 slip rings or 3 slip rings?
That determines everything, doesn't it?
It does, indeed. It's interesting because I personally always enjoyed troubleshooting wound rotor motors, and the reason being is that we start comparing that to the classic squirrel cage induction, which we've been talking about. A wound rotor motor actually has windings on the rotor. You have access to put signals onto that rotor and test it. And it's we like to make this comparison of a transformer versus a motor, right? And you have the stator and the rotor. To me, it's the wound rotor motor offers almost the perfect analogy of transformer conversation as it applies to the motor. Because it's the same induction principle. Stator windings, rotating magnetic fields, inducing onto, instead of rotor bars, they're inducing it onto windings. These windings on the rotor are wound in a wire delta configuration, connected to some slip rings. But the thing that we can't do is we can't heat up winding and insulation like you can heat up a rotor bar, right? Part of the simplicity and robustness of a squirrel cage induction motor is it's steel and copper, or steel and aluminum. That goes through a lot of severe heating. You cannot do that to the windings on a wound rotor motor, or it'll melt the insulation, because now we're talking about windings with insulation. So you have to control the current, and they do that through an external resistor bank connected to that rotor circuit. It's an interesting construction.
Right, so you kind of went through the construction of it. The stator is pretty much the same as what it would be.
It's exactly the same, no difference at all.
Induction motor. The rotor is slightly different, like you had said, that it's wound, maybe has wires versus copper bars.
Yes. And there's temperature requirements on that, same as on the stator. If it's a class F at 155, that rotor, keep in mind, the rotor undergoes probably the most intense heating through a startup process. And if you let that uncontrolled, if like the resistor banks failed and didn't reduce the current to a controllable manner, you will melt that rotor right away.
And so then there's also slip rings and brushes. So we're kind of introducing more potential problems with troubleshooting because of all these additional components. So it's not as simple as an induction motor, is it?
It is not. It is not.
And then you have a rheostat, which cuts out resistance, able to control it, because you're putting resistance on the actual rotor for speed control.
Absolutely, and keep in mind, there's a variety of things that occur in the operation of this motor. When you first start it, the resistor bank is 100% intact, right? So you've got contactors that automatically will cut those resistors out. So the maximum resistance is paralleled with the rotor circuit, the rotor windings, during startup. So with that maximum resistance, higher resistance, lower current, they're able to control the current and therefore control the heating, and it also has a direct impact on the torque. So they can they can handle a whole lot of torque. One of the things that's unique about these, we'll talk about the advantages. But as the motor starts to turn and counter electric motive force starts to become a factor, then they start to cut these contacts in, which basically short the resistor bank, and less resistance, you can put in more current. Everything controls itself. It's a very good and amazing torque. I mean, we're talking 300% of full load torque that these motors can handle.
Maybe that's a good entranceway into what types of motors. First off, we know that these represent probably 5 to 10% of the motors in the industry. So it's a very small population. But where would they be utilized at?
We've seen them a lot in things like, cranes. Cranes are very popular because with the crane, you have, you're picking up massive loads, you need a high amount of a torque, but you want very controllable speed. And these are ultimately great speed control devices. Once you cut out the resistors, what's left at the end is a variable rheostat, right? So the crane operator can simply, be varying the resistance on the rotor, varying the torque, varying the speed at which he's lifting things. Another real popular application, we saw this a lot up in the oil sands of Canada. They got these massive conveyor belts. I'm talking as far as the eye can see. Can you imagine starting that conveyor belt up with, basically oil sands laying all over the top of it? The amount of torque is unbelievable, right? And they might have 10, 15, a high number of these wound rotor motors all trying to move this conveyor belt. So that's another really big use of them. But we've also seen it in pumps. There's just, so it's not
elevators.
Elevators are another popular use of them. Some elevators are DC because they like carbon dust, and that's their choice. But carbon dust on a commutator is a lot different than carbon dust on a slip ring, right? So
talking about belts, we have an excellent case study where it was just a simple human error where they mislabeled 2 and 5. So when they tied that motor together, which was a wound rotor motor, it would immediately show it would trip.
Yes, it will.
And the inductance was complete inductive imbalance of close to 100%.
Yeah, it's massive.
What caused that? So
here's the scary thing about this. I remember this case study you were talking about. It was a great online YouTube. We did YouTube on it. What was interesting is within the last couple months, we had a phone call from a motor repair shop and asking the question, say, hey, do we think that offline inductance measurements should see a reversed coil, right? And when you mentioned a 2 and 5, well, if you think about the numbers on a 6-winding motor, it's 1, 2, 3, 4, 5, 6, right? A lot of times
4, 5, 6 are tied together
in a normal configuration. Yes. Yeah. It's a Y-wound, internally connected, right? But what happens if you switch? So winding 1 is 1 and 4, 2 and 5, 3 and 6, right? That's how the windings are laid in.
4, 2, 6 now.
Yes, and so instead of connecting our power to 1, 2, and 3, it's 1, 6, and 3 or whatever, right?
That's a bad day.
It's a bad day, right?
That's where you get the new guy, right, to start that motor.
We always say, if you're not sure, let the new guy start the motor. And here's the magic, right? Think about the resistance measurements we take, right? You're applying we talk about power circuit assessment. When you apply a DC signal into a 3-phase stator, you're just traveling the path of the windings, right, from one phase to the next. Well, just because you inverted a coil, it doesn't change the conductive path. So resistively, it's perfect. And what happens is, inductance is a little bit more magical to some of the, if you haven't been through a lot of training, through any kind of certification for motor analysis or whatever, inductance is a little more magical than resistance. Resistance is simple. You apply a voltage across and you figure out what is the resistance.
We always go through the inductance equation, right?
We do.
So there's quite a bit there's a lot of variables in that inductance equation.
There are.
That, like you said, if you're going in opposite direction, you will change your inductance.
Oh, big time. Now, when you invert that coil, you are bucking the normal design of that phase. And so when you buck that, it's like all of a sudden you've got an electric brake that's being applied every time that coil is energized. You can imagine the massive influence it's going to make on the motor starting. And as a result, you say it trips, it absolutely trips. If I remember right, they were blowing fuses right and left.
Yeah, a couple thousand per fuse.
Right.
And like you said, they did resistance checks and it was fine.
And that causes them sometimes to say, hey, if it's resistively balanced, everything should be fine. Not the case. Yeah. So be aware that if you get a motor that's not labeled, the winding, if you've got a 6-lead, 9-lead motor and there's no labels, do your homework.
Yeah.
Make sure that you know which ones you're connecting, because it's not going to be friendly. And inductance is a great measurement of that.
So what are some of the benefits? You mentioned a little bit of excellent speed control.
Yeah, in fact, through our case study, we've kind of talked a lot about it, but excellent speed control for something like a crane or a conveyor if they wanted to speed that up. Obviously, high torque situations. Another great case study or C-story that I got involved with in local Tampa, actually. There's a metal, recycling plant, right? So they basically, you take your old metal and you deliver it, they give you some cash, and they run it through, guess what? A wound rotor motor shredder. Well, this is no small wound rotor motor shredder. They were taking 454 big block engines and running it through this shredder. And let me tell you, remember, you're never supposed to be standing next to a cabinet when you start a motor, and I live by that, right? So we set up our equipment. We were going to do an in-rush startup, one of my favorite tests. I wanted to see what this wound rotor motor looked like when they started it up. Well, again, it starts at full load. Whatever trash is on the conveyor belt going into this shredder, it's still there, right? So they started this thing up, and I set my equipment up pre-trigger, and I walked away. And when that engine block hit that motor, I thought the building was going to come apart. It's a lot of torque. And like I said, they're designed to start right off the bat with as much as 300% of full load torque. So hats off to the designers on that. But it was a great case study in that, we were able to actually identify, weaknesses in the rotor circuit that was creating some, high vibration, and it was actually a magnetically induced vibration. So it was great, but a great experience for me to see that kind of impact, and the fact that the motor, it moaned and groaned, but it kept going. It made it to the end. So, but yeah, high torque applications are a big deal.
Yeah. What about concerns? What are some of the negatives of a wound rotor motor? Because they're more complicated, maybe the maintenance strategy is a bit more complicated.
Can I tell you, anytime there's carbon brushes, I get a little tick, in my neck, because if you've never been on a submarine, it's if you haven't been covered from head to toe in carbon dust, you just have not lived. So if you're a maintenance reliability guy and you see the electricians going into the local wound rotor or DC motor to clean out the carbon dust, volunteer. Go in there with them and get covered with carbon dust once, just to say you've done it.
I can't really ever understand your C-stories, because surface guys didn't get involved with any of that type of stuff. We were more refined than that.
Yeah, you guys were overpopulated.
We had
and had fresh air.
It was Grey Poupon.
It was, yeah. Well, here's the other thing, right? We talk about heating, right? With the air inside a submarine isn't the same quality as the air outside of a carrier. So that clean air did make a big difference, and I can tell you that when it comes to a big concern is when you're looking at these wound rotor motors, and you're looking at the slip rings, they need to be a chocolatey brown with a very conducive surface. I always suggest, hey, if you're not doing a visual inspection of a wound rotor motor on a weekly basis, you're missing an opportunity to see something going wrong. Any kind of chemical can attack that surface of the slip ring. It'll deteriorate the brush, and from one week to the next, you'll see a third of your brush length gone. And that carbon dust goes someplace. Unfortunately, it likes to pack itself in the stator windings or the rotor windings, and that causes a ground situation.
On a carrier, we would come into that because you're sucking in basically exhaust fumes from JP5 fuel or the fuel of the jet plane. So you would, they go off the deck and then you're blowing in outside air. So you would get some of those contaminants in there, and you might get that on the slip rings. And then also, we've been into many facilities around the world and locally and domestically, and not everything is in...
you don't eat off the floor.
Sometimes it's not as clean.
And can I tell you that the Navy was big on commutator slip ring handbooks and stuff, and great material, and we were educated to the ends of their capability.
Well, they used a lot.
They did. But can I tell you that the commutator slip ring handbook, it's available to everybody that's listening to us today. You go online and you look at that, you can find that. It's a great book. It's got pictures. It allows you to kind of get an idea of what might be going on with your slip rings and brush configuration.
About YouTube anything now.
These days, yeah. Even the Todd and Noah show, I think.
Yeah, you could absolutely. Except that. You can only find that on CBM Connect.
That's where we need to go.
And PDMA.com. So we talked about concerns. What about collection of data? How would we collect data for wound rotor motors?
Yeah, and I tell you,
so for the stator, what are we going to look at?
No difference. For the stator, we're going to look for voltage imbalances, current imbalances.
Okay, so
when you shut down,
like an induction motor, like
exactly the same.
Rotor now.
Rotor,
different.
It is different. It offers a whole breadth of new things to look at, which of course can be problematic in itself.
So online, pole pass sidebands, can you monitor them?
You can. Even though they're not rotor bars, there's still slip involved.
But it's not at the same, like it was a rotor bar, not the same level.
Our general general guideline to those that are using, motor current signature analysis or pole pass frequency sidebands is don't use the standard 36, 45, 54 dB differential alarm set points for a wound rotor motor. Establish a baseline and trend it from there, right? Hopefully you're testing early enough that you have it when it's considered normal. So when that sideband starts to creep up, and you and I have seen case studies involved in this, it's going to make you early aware that there's a problem and you can go fix it. Like I mentioned, I love troubleshooting wound rotor motors because we can send signals to the rotor, we can send signals to the stator, we can send signals to the resistor bank. I don't think it's that difficult to isolate the source, but then determining the severity, sometimes that's where you have to reach out to professionals and try to come up with a new idea. Do we have time for a case study?
Well, yes.
It's a C-story on a wound rotor motor, differently than the last, not a shredder, but it was a pump in the cement industry. And we get called in because they said, hey, our brushes are disappearing. Now, it's not a magic trick. The brushes were going from a 3-4 inch, long brush to a 1 inch, about to dive into this, dig into the slip ring in a very short period of time. We show up with our technology, and you know how we always have 6 fault zone, power quality, power circuit, insulation, stator, rotor. I've always talked about being another one, which is called It's Not the Motor. Did I miss that one? I speak a little fast sometimes. But in this situation, it was one of those, it's not the motor, right? So we're checking the rotor windings and the stator windings. We're doing all this measurement, and we're clearing everything right and left. The resistor bank's good. We go through an inrush startup test, and that's even good. It ended up being a bad brush design. Now, what's weird about it to me, that's very simple. We'll just call the boys at the brush manufacturer for current density and make sure we're using the right thing. They did that, and it still wasn't the problem. What was happening is either the first or the second slip ring would suddenly start eating up one brush, and it wasn't always the same slip ring. Well, they ended up having to go to a different brush design with a diagonal slit, so instead of just one piece of carbon, there was multiple pieces of carbon. What it allowed the environment to do is to change the pressure on the brush more appropriately. Every brush has a spring tension on it. We used to measure that in the Navy, right? So this allowed a more even distribution of the brush pressure, but it took like a retired engineer to say, hey, you're using the wrong brush design. But at the end of the day, it wasn't the motor.
Right.
They could have replaced the motor.
Brushes are very cheap to replace.
Compared to a motor, absolutely.
They're dollars versus thousands of dollars. So now offline, what would you for the rotor circuit? Because you have the resistor bank. You can test that, correct?
Oh, absolutely. Yeah, there's cables coming in connecting to the.
Where would we tap off to test that?
Almost always, it's at the slip rings themselves.
At the slip rings.
Yeah, we'll lift the brushes. Connect to a good solid lug that's connected to the brush box. Right back to the resistor bank.
Right back.
Now, for the resistor bank, inductance is not our focus. All right, inductance is an AC test. This is a purely resistive circuit. We focus on resistance.
And what about for the rotor itself? Is that
for the rotor? Now we're going back to the slip rings to go into the rotor field, right? And that's can be kind of magical sometimes.
Yeah. So you almost have to have a specialty device or look at it online through Emacs.
Right. You know what we hear coming back from the customer base, and they get excited to tell us these things. The things that they do to help them, more purely get on the slip rings. Some of them will use the bar-to-bar test leads, so they're just pressing them on, right? So that's one thing. The other time they'll do is they'll actually wrap a copper winding around the slip ring and connect to that, because that's a good contact.
A lot of times they'll just use the online, and then if there is an issue, then go into the more in-depth.
To me, the most efficient approach, use what you've got. Because here's the thing, keep in mind that the frequency flowing through the rotor, even if it starts at 60 when you first start the motor, by the time you're up to speed, the frequency going between the brush box and the rotor, because of the slip now, right, the rotor starts to catch up to the stator. It's under 7 hertz, right? So certain current probes, keep in mind, if you're measuring this, you may not even be able to see that, because a lot of times the iron core probes have a frequency response above 7 hertz, and the frequency in that rotor will be down around 5 to 7 hertz. So you may have to think about using a Hall effect probe if you're going to get to that current. But we love to watch the inrush startup, because keep in mind, remember I talked about the contactors? Well, when you're measuring the current through the rotor, it's so amazing how you can see each contactor closing and taking the resistors out through the startup. It is so easy to see a problem with that.
As it builds up speed.
Right, you have a high current, it starts to fall, and you can see it bounce. And you can do inrush from the stator as well. And no question about it, recording an inrush connected to the stator windings is almost always easier. You have easier access. But if you have access to the cable run between the slip ring and the resistor bank, at some point, get a baseline inrush on that, because it is absolutely amazing to look at. We also have a good, on the data interpretation book that we distribute, there's a really good indicator of that wound rotor, rotor startup circuit.
Okay, so that kind of takes us through two of them, and we're going to make this kind of a part one of two parts, because I think there's a little bit more, and we don't want to make it too large. We're already about 35, 40 minutes into this one, so that's probably enough time spent on this. So thank you for all of your intellect and sharing with us your thoughts on case studies and on wound rotor motors,
C-stories,
induction motors, and C-stories, and all of your worldly travels, testing these types of things and sharing your experiences with us. And we hope that collectively as a group, as you're listening to us, that you'd get just a small tidbit to make your tomorrow a little bit easier, right? Because that's really the whole purpose behind us doing this, is to give you a little bit of information that hopefully helps you tomorrow or the next day say, oh, I remember hearing that, and then putting it to an application or putting it to work so that you can have a better tomorrow or a more effective tomorrow or a safer tomorrow. So we appreciate your time. Thank you so much. Once again, that's Todd Gunderson and Noah Bethel, and this is the end of part one of Induction, or Specialty Motors Induction and Wound Rotor Motor, taking the mystery out of electric motors. Thank you.
Thank you for joining us for this episode of the Todd and Noah Show. We'll be back for another episode very soon. In between, we hope to see you in the Mobius Connect online community, where you can network, learn, and share with Todd and Noah and other industry professionals at mobiusconnect.com, and we will see you there soon.